Okay, this video is all about polynomial functions. So I'm going to start off with your definitions and theorems page for the definition of a polynomial. So I'm in page 4 of Unit 2's definitions and theorems. What we want to look at is the formal definition of a polynomial, and that is this second bullet point. This is the equation for a polynomial. So we're used to seeing powers of 1s, 2s, and maybe a 3, but a polynomial can be as large as we want it. And this power right here is called a degree, and it tells us what degree, sorry, it's called a degree, but it tells us how large the polynomial is, right? It will help us figure out how many zeros you can have. So you can have, if you have a power of 5 function, you can have a maximum of 5 zeros on the graph. We'll use this information for a lot of the stuff that we do. So first of all, it's very important that the graphs that we're looking at are very continuous, and that's because they're smooth and they're connected. You can graph them without lifting up a pen from your paper, and there's no cusps like an absolute value function. From the equation, what's the important part that we're going to focus on right now is called a leading term. It's the first coefficient and power in our equation. It has the highest power. So remember that the highest power is the degree. The whole thing before the plus sign is a term. Actually, everything in between a plus sign is called a term. This is the leading term, and the number in front, or the coefficient of the term, is our leading coefficient. And the definition for that is right here. It's the AN. It's the leading coefficient. Why is this important? This is important because it tells us what the end of our graph looks like. Whether the arrows are both going the same direction, whether they're going opposite directions, whether it's positive or negative. It gives us all that information from just this first term. That's called end behavior of a graph. So that's this next definition that we have. Tells us how the graph reacts based on the leading term. So I'm going to put some examples up here so that you can see. I like to use graphic organizers, so I'll draw a little box a couple of times. If you don't like to do that, that's okay. Just going to label and identify things, just like your homework. This looks like the box off of your homework. Leading coefficient, leading term. Okay. So the first example that I have for you is, let's say f of x is equal to 5x to the 5th minus 2x cubed plus 3x plus 7. Okay, so we're going to focus in on the degree, the leading term, and the leading coefficient. The leading term is the term with the highest exponent, so 5x to the 5th. The coefficient is the number connected to the x, right? So the 5 in this case. It is important that the leading coefficient takes the sign that it comes with. So if it was a negative 5x to the 5th, it would be a negative 5. And the degree is the highest power, which is on the leading term, which is 5. You don't have to do this part on your homework, but I do want you to know that this is called a quintic function. A power of 5 is a quintic. While we're talking about what names are, the name polynomial just means many terms. So the definition reflects that for us. Okay, the next function, let's say g of x is equal to 3 plus 2x squared minus 2x cubed minus 4x to the fourth. Okay, I'm trying to trick you on this one. Please be careful. It's not always the first term that is our leading term. It is the term with the highest power. So in this case, I wrote it in a different order so that you can find the highest power of 4. So this is a degree 4 function, which is called a quartic function. It has a leading term of -4, and the whole thing is it has a leading coefficient of -4, and the whole thing is our leading term, -4x to the power of 4. So this is a 4th degree polynomial, or a quartic function. Okay, lastly, let's do a cubic function. So we should have a degree of 3. Let's see if I can do that for you. Let's see. 6x minus 2x cubed minus 4. Okay, I wrote it in the wrong order again just to make you identify it. But normally we write them from the highest power to the lowest power. Okay, so in this case, here's our leading term, -2x cubed. Again, that degree comes from this high power right here. It is a cubic function, and it has a leading term of -2. Okay, now again, identifying this information is going to be beneficial to figuring out what the end behavior looks like. It does use the leading term, so we need to think about the leading term for a minute. One thing I didn't ask you in this section was whether the function was an even or odd function. You can identify even and odd based on their degree. So the highest power tells you what type of function. So any function that has an odd number, like 5 or 3, these are going to be odd functions. So odd functions have odd powers, or odd degree. Even functions have an even degree. So in our example, this quartic function is an even function. Another even function would be a quadratic function. Oops. Another odd function would be a linear function. Okay? Any even power is an even degree, any odd power is an odd degree. Why do we need to know that? Well, we need to know that because of our end behavior table. I'm just going to pull up the table for you. I put it on here so that you have it. Just keep in mind that this graphic organizer always writes as x approaches -infinity first, and as x is approaching +infinity second. They write it left to right. I write mine backwards, so just keep in mind when you're looking at your homework, I write x as positive first. So we found all of this information to make this chart. We have two different types of function, even powered function and odd powered function. If you look at the even powered function, we have ending arrows on our function. If it's a positive function, which means the leading term is positive, so in our example, R4, our even function was negative, right? That's because of the -4 in the front. But sometimes you can have a positive function. If you have a positive function, both of your arrows point to positive infinity. So we say the left hand and right hand behavior, or the end behavior of our polynomial. So as the x's are going to positive infinity, my graph is pointing up, which means it's going to positive infinity. So we say as x approaches infinity, the graph, f of x, approaches infinity. The same thing on the left-hand side. As my x's get smaller, my graph is getting bigger. So as x goes to negative infinity, the graph goes to positive infinity. So that's how you read this. It's all about the direction of the arrows, and the y, the infinity that you're filling in is determining the y values. Look how the negative ones, they both point negative. That's because we reflected this positive function, and now we're pointing towards negative infinity. So both of these end behaviors is negative infinity. An odd function is special because the arrows point opposite directions. That's how I remember which one is which. My odd function has an odd power. My end behavior is opposite. Notice that on the positive side of the x-axis, the positive function goes to positive infinity. But on the negative side on the x-axis, it goes to negative infinity. And then when we reflect that over using a negative coefficient, the opposite happens. So a positive infinity goes to negative infinity. That's this line right here. As x approaches positive infinity, y approaches negative infinity. And then this line, as x approaches negative infinity on this side, y is approaching positive infinity. Now I know this kind of sounds complicated because I'm giving you a lot of information, but what you're going to do is look at your problems, match it with one of these four options, and then the answer is written on the page. So we're just trying to figure out either from a graph or from an equation what the end behavior looks like. So I have some examples for you for end behavior. So now I can give you just an equation of a function, and you can tell me what the graph is going to look like by finding the end behavior. So my first example is 4x cubed minus 2x plus 1 is equal to g of x. Okay, first you want to identify your leading term. Here it is. It has a power of 3. So you want to ask yourself, is 3 even or odd? Well, this is an odd function. Sorry about my camera. Now we want to look at the leading term, the 4, and ask yourself, is it positive or negative? Well, this 4 is positive. So we have an odd positive function. So I'm going to go to my chart. This chart has all the information. Here's the odd functions. Here's the positive functions. So this graph is odd positive. This is basically what it looks like. It might be a little different in the middle, but this is what the arrows look like. So this is the answer right here. For your homework, you just have to fill in the infinities at the end. For me, I'm going to have to write the whole thing. And remember, I write it backwards, so I'm going to write as x approaches infinity, f of x, our positive side of the graph, is pointing in the positive direction. But as x approaches the negative smaller numbers, my graph, y, approaches also negative smaller numbers. So negative infinity. And that's what I'm looking for. Again, you're filling in just these last two spots. Okay, let's do another one. Let's say h of x is equal to, I don't even know. Oh, negative 2x to the 6th minus x cubed plus 2. Okay, we care only about the highest degree. So the highest power is a 6. That happens to be an even number, so this is an even function. Okay, the coefficient of this term is our leading coefficient, and it is negative, so this graph has been reflected, and now it's a negative even function. So on my chart, I'm going to come over here. I want even functions, and I want a negative even function, so they overlap is here. This is what the graph looks like. If you notice, both of the arrows go the same direction, and they both go to negative infinity. So as x approaches infinity, as my x's get bigger, my y's get smaller. I left my negative off, sorry. So they approach negative infinity. But as my x's approach negative infinity, my y's also approach negative infinity. This will help you find limits once you get to calculus. So this notation is important to help you remember, to help you set up for limits. Okay, you should be able to do those without a problem. We need the end behavior to figure out eventually how to graph. So that's one thing that we'll use on when we get to graphing. Okay, now let's talk about our theorems here at the bottom. We have two theorems. We have a zero theorem and a factor theorem. Both of these combined say that if I factor out my polynomial, I can replace the f of x with a 0, solve for my x-intercepts, and then also use factored form to help me find multiplicity. That's not what this says, but you can factor it out and your factors can become your zeros. So you set them equal to 0 and solve, and that is your 0 of your graph. So remember that p of x equals, when you have parentheses, you usually have an x here. This is factored form. We're going to use this to find multiplicity. But you can also use factored form, according to this theorem, to find out where your graph crosses the x-axis. So that's a great thing that we can use. The intermediate value theorem says that I can pick any 2 points on the graph because it's a polynomial, because it's connected, and I can figure out that there is a 0 in between. So for example, that's another way to find your zeros, or to check how you can check what's happening around your zeros by finding a positive and negative, and it tells you that once your polynomial is positive and negative, then there has to exist a 0 in between because it's crossing the x-axis to be positive and negative. We don't usually use that theorem in what we're about to do, but you will use it in pre-cal and calculus. What do I need from this page? Even and odd. Well, I didn't put a multiplicity on here. Well, I can tell you what it means. Multiplicity is the behavior of a 0. So a 0 is an x-intercept. That can be found by factoring, but the multiplicity tells us the behavior of a 0 on the graph. It can be found by looking at the power in factored form. Okay. So we're going to factor a couple of equations. We'll find their multiplicity and their effect. And I'm a graphic organizer person, so problems on your homework have it in a little box. You don't have to organize it that way. That's just how I like to organize it. Before I do that, I want to show you there's 3 outcomes that we can have that we're going to focus on. You can have a power of 1 on your factored form. So this is an idea of a power of 1. We don't usually write a power there, but it does have a power of 1. So using the zero factor theorem, we can say that we have a 0 at positive 3. So you set this equal to 0, x minus 3 equals 0, and solve, which gives us x equals positive 3. So my graph here with a power of 1 is going to cross at this 0. And it can cross negative to positive or positive to negative. It doesn't matter. But if I have a power of 2 on my factor, we still have a 0 at 3. But this time, we're going to bounce off the graph. You can again bounce on the top or bounce on the bottom, and we'll figure that out in just a minute. So what's going to happen is you're going to approach the graph. It's going to touch the 0. And then instead of going through the graph, it's actually going to bounce back up and go the same direction. So you can call this a bounce or a touch. Either one is correct. But when we have a power of 3 in our exponent, then it gets to look a little weird. So we're still crossing at x equals 3. We're still going to cross because it's an odd power. Any odd power crosses, any even power is going to bounce. But when we cross, because it's a power of 3, it gives off a point of inflection or a cubic looking function. So it changes concavity right here. Okay. Now that's helpful when you're trying to write a functions equation and when you're trying to graph a function. So we're going to find some factors, and then in the next video I'll show you how to graph. This one's getting a little long. Okay. So we're going to factor polynomials. Now there are many ways you can factor a polynomial. We're just going to show you a couple of them. Okay, so let's start off with what happens if I have 2 terms. Man, I keep forgetting my f of x. Okay, so we have f of x equals x to the 5th minus 9x cubed. If you have 2 terms, find the GCF. So find out what they have in common. You want to check to see if their numbers are divisible by each other, but we have a 1 and a 9, so we can't factor out any numbers. But they both have x's, so you always take the smallest power of x's because there's 3 in here and 3 in here, but there's not 5 in here. So we're going to pull out the smallest power, which is x to the cubed. So we're going to put it outside of our parentheses. I can replace the f of x with a 0 because I'm going to start to solve. That's what my 0 factor theorem says, actually factor theorem, right? Left inside we have 2 x's, x squared, and then we took the x cubed out, so the only thing remaining is the 9. Now, once you get to this step, before you say you're done, always check to see if this factor is perfect. By perfect, I mean I can find the square root of x squared, I can find the square root of 9, and it has a subtraction sign. This is the difference of 2 squares. What we're going to do here is split the x, split the 9. 9 is 3 times 3. 1 is positive, 1 is negative. Don't lose this x cubed on the outside. Okay, so now the 0 product theorem says that I can set each one of these equal to 0. And solve to find my zeros. So this is x equals 0, x equals negative 3, x equals positive 3. On your homework, I have little charts for you to fill in to make it easier for you. I think they say multiplicity, 0 first, sorry. 0 multiplicity effect. So each one of these zeros gets a space in here. So we have 0, positive, and negative 3. Now you're going to go back to its factored form and look at the powers on the factors. At 0, we have a power of 3, so this is a multiplicity of 3. At negative and positive 3, they both have a power of 1, so their multiplicity is 1. Now, because they all have odd multiplicities, they all cross the x-axis. If you had an even multiplicity, you would write bounce, because it's going to touch it and come back up. But these are all going to cross straight through the axis. This one does cross a little fancy because it's a power of 3, but that's okay. Okay, let's do another one. This time I have well, I have a f of x equals x cubed plus 4x squared minus x minus 4. So I should be able to find at least 3 zeros, at most 3 zeros, because of this power of 3. If you want to check that theory, this one has a degree of 5, and I have 3, 4, 5 zeros. Okay, so this has 4 terms. When you have 4 terms, it's probably easiest to do factor by grouping. So we're going to set this up so that the first 2 terms are in one group and the last 2 terms are in another group. You can also do this with a factor of 3, a trinomial with 3 terms. What am I doing? Oh, so now once you have them grouped, you're looking for a greatest common factor, just like we did with 2 terms, because now we have 2 terms, right? So the numbers don't match. They're not divisible by the same thing, except for 1. But I can pull out a power of x squared. That gives me x plus 4 left. And then we want this to match this, but it has negatives in it. So that's what I'm going to pull out of the function. That's the greatest common factor, is a negative. Actually, anytime this one is leading with a negative or this one is leading with a negative, you're going to want to pull that out. Okay, that leaves positive x and positive 4. Now, if this x plus 4 does not match this x plus 4, you've done something wrong and you need to recheck your math. If it does match, you can keep going. So you have x squared minus, and this is 1, even though I didn't write it originally, and x plus 4. Okay, before we can say we're done, we have to check for perfect squares. So this one's a plus sign. I don't have to look at it anymore. This one is a minus sign. So can I split the x and the 1? The answer is yes. I can split them by finding their square root. So split the x's, split the 1, because 1 times 1 is 1. One's positive, one's negative. And here we go. There are your zeros. So the zeros for this function. Now, some of you might have noticed that when I wrote these, basically what happened was you changed your sign. That's going to happen every time. If you have a number in front of the x, you'll get a fraction, and that's okay. If you have an x outside, and it has to have an x, just a number does nothing. But if there's an x outside, then it's always going to give you a 0. So this 0 is at -1, +1, and -4. The multiplicity, they each have a power of 1. Well, okay. So the multiplicity is 1, and because they're all odd, they're going to cross. Okay, I think you can finish that part of your homework. I'm going to end this video and do graphing on the next video. But basically, we're going to take all of this information and we're going to graph our polynomials.